So now let R1 and R2 denote the risky returns on these two assets. What's my portfolio return? Well, you can see the various components here. I have 1 over sigma 1 dollars invested in the first asset, earning a return, random return of R1. I'm short 1 over sigma 2. I shorted the second asset, and then I have a T-bill position, which could be plus or minus. I don't know. Now, what's the expected return? Well, the expected return is positive. This calculation was designed so that the expected return was the difference in Sharpe ratios. And so what we see is that we have an expected return equal to a positive number. It cost us nothing to construct this portfolio, and yet we expect to make a profit. Well, that's an arbitrage. But it can't be an arbitrage until we know what the variance is. Well, we're going to show just now that the variance of this is 0. And if we show that, and I'll show that on the next slide, then we will have had an arbitrage which tells us it must be the case that the Sharpe ratios are indeed the same. So let's show that the variance is 0. And that'll prove that we have an arbitrage, and therefore it must be that the Sharpe ratios are the same. The calculation is that if R1 and R2 are perfectly correlated, I can write R1 as mu1 plus sigma 1 times a normal, and R2 equal to mu2 plus sigma 2 times a normal. Notice I'm using the same normal because they're perfectly correlated. Now if I look at sigma 2 R1 minus sigma 1 R2, which is the numerator of the expression we have here. Notice that if I take this term and I just consolidate it, put it over the common denominator, sigma 1, sigma 2, what I'm working with is the sigma 2 R1 minus sigma 1 R2. The numerator of that ends up having no z in it because the z terms cancel. I get sigma 2 mu 1 minus sigma 1 mu 2 divided. And so the term I was dealing with before was this one. It's non-random. In other words, if I have two perfectly correlated assets, this R, although it looks random, it's not random. R1 and R2 are perfectly correlated returns, and because they're perfectly correlated, their randomness cancels out. And so, in fact, R, not only does it have an expected return equal to the difference in Sharpe ratios, it has a return that's always equal to the difference in Sharpe ratios, and that's our arbitrage. So what we can then say, if we have two assets with the same Sharpe ratio, is that the relationship between the mean and the variance is predictable. So one way of saying that is if I know that a certain asset has a Sharpe ratio of S, then its mean and standard deviation and risk-free rate have to satisfy this formula. This, of course, is just a rewriting of the Sharpe ratio definition. But it tells you that if you know the Sharpe ratio, the risk-free rate, and sigma, you know the mean return. Another important implication of this is if I have two perfectly correlated assets, we know they have the same Sharpe ratio, and therefore that equation produces this, that the difference in means has to be the differences in standard deviations times the Sharpe ratio. Namely, if I know the Sharpe ratio of two assets, and for one I know both the mean and the standard deviation. For the other, I only know the standard deviation. I can predict the mean of that other asset. So another way of saying this is that for assets with a given Sharpe ratio, every extra unit of standard deviation translates into SR units of extra mean. This is just another way of interpreting that. The Sharpe ratio is the number of units of extra return you get per unit of extra risk. So if one imagined that sigma 2 minus sigma 1 is 100 basis points, sigma 2, the asset has 100 basis points of extra risk, it's telling me that I should get an expected return that's equal to 100 basis points times whatever the Sharpe ratio is.